Okay, good. So it will be recorded for either from you if you want to review the challenge kickoff, or for the people of the CIU that are absent to review what we will launch and what we will discuss today. The challenge provider is ArcelorMittal, as we said already previously, but I will leave Akshay introduce himself, his company, and the challenge by itself. The sequence will be divided into logically two parts, an introduction, an explanation about the topic, and as much as we have time, also share with you any questions you may have regarding the challenge. I would like to separate the questions that are technical due to what we will use as a tool, the way we will conduct the inventive design process, which will be my part when we will be together in course and in French. But while we are in this session, it's much more questions you would have dedicated to understand the topic, while Akshay is here for answering. Okay? So Akshay, it's all yours, and
Okay.
we welcome you here too.
Thank you, Denny. So thank you everyone for having me here, and thank you for giving this opportunity. So my name is Akshay Bansal, and I'm from ArcelorMittal. So just as a quick introduction to who I am. So my role at ArcelorMittal is at the Global R&D. I'm currently leading the Global R&D Energy Program. So a program typically consists of more than 30, 40 different projects, R&D projects, running at any given time. So I'm based out of Mézières-les-Metz, in not too far from Metz, so roughly 1 hour from here. And I've been working there for roughly 10 years now. So my background is actually, I'm also an Insaien. I'm from INSA Rouen. I finished my graduation almost more than 10 years ago now. And then after that, I did my PhD in Nancy in industrial processes, energy systems and energy processes. And since then, I have different roles at ArcelorMittal. One is that of the energy program, but I also have that of, I'm a researcher. I'm a scientific researcher at ArcelorMittal Global R&D. And at the same time, I'm also coordinating what has to do with the technical creativity and open innovation. So technical creativity, all of you are supposed to be also part of that. And this ECIU challenge is in a way a mix of both of them. Okay. So steel, everyone knows steel. I heard most of you have mechanical or electrical or energy related backgrounds. I don't know of the backgrounds from the ECIU, but I'm assuming some of you have already had some flavor of steel. So steel is used almost everywhere in your daily life. Even in this room, you can see steel in different areas, from construction to automobile, to the train that I took this morning to come from Metz, to the tram as well from the train station to here. So the rails that you are using, the cycles, everything has some way, some steel in it. So you can start to imagine life without steel, and you will probably come to a very quick conclusion that it will be very difficult to have a civilized life that we are trying to have in the world. So ArcelorMittal, who are we? We are 150,000 people all across the world. We are spread across 15, if I remember, 15 or 16 different countries where we have installations of production. And then we are present in more than 60 different countries where we are present in terms of sales and services and so on. So we are not only steel producer, but we also have mines, iron ore mines, coal mines, and so on. So that means we have vertical integration across our production. Just a second. Okay, so we are present in Europe, of course. It's our historical base. But we are also present in different areas across the world, in North America, in Canada, in the US, in Mexico, in South America. We have operations in Brazil, Argentina, and so on. In Africa, we have different countries, South Africa, Morocco, Liberia, and other places, as well as in Asia, in China, and India. So these are all our operations outside Europe, and within Europe, we are present almost in all the countries, including France, but also Luxembourg, Germany, Belgium, Spain, and so on. So we are currently the second largest producer of steel in the world. The first is Bao Steel, which produces roughly 120 million tons of steel. So ArcelorMittal produces roughly 60 to 70 million tons. It depends on the year. And you can see that it's really fragmented. So that means in the world, typically we produce between around 1.5 billion tons of steel every year. The largest is 100 million or 120 million. So that means that it's really spread out. There are many different players inside the steel industry, and amongst all of those players, ArcelorMittal is right now the second in terms of production. Okay, just some numbers, but you can take that up in different. If you just Google or ChatGPT ArcelorMittal, you'll find all of these numbers. Just to say that typically the overall annual sales is between $60 to $80 billion per year. Okay, we are committed to a net carbon neutral target by 2050. We have a full roadmap which has been published in order to achieve that in Europe, but also all across our group. So that means we want to be in the next 25 years. So 25 years is basically tomorrow for us, because any major transition, and we're not only talking about changing the way that we're doing, but we're talking about transforming the things that we've been doing for the last 200 years. We need to change that in the next 25. So we are definitely counting on the new colleagues, just like yourselves, who will play an important role in achieving this target, in at the same time achieving the technological and the scientific targets, the economic targets, but also the carbon neutrality targets. So that means the environmental targets. So we need to be able to combine all of those. Okay, there are some examples here that you can see. We have, for example, something that really, let's say, motivated me are some first of its kind solutions which have been actually implemented, where ArcelorMittal has really invested a lot of their resources in terms of time, money, energy, research, that you see today was started maybe 10 to 15 to 20 years before. So we always need to be preparing for the next 20 years. And one example could be Steel which was installed in Belgium, in our plant in Ghent, where we are taking the off gas coming from blast furnaces. Some people in the room know what blast furnaces are. So blast furnace is a way to reduce iron ore. And when we're doing that, it produces a certain kind of gas, which is called the blast furnace gas. So the blast furnace gas has some molecules, carbon-based molecules. Until now, let's say 5 years ago, that gas was used in our power plants, but that's it. So now today we have new solutions come in, and which have been demonstrated and industrialized, which use this blast furnace gas and are taken to a bioreactor. We produce bioethanol out of it. So till now, a gas which was not, let's say, valorized fully, it is now fully valorized, and in ways that were not, let's say, typical of steel industry. That's the example that you see in first smart carbon capture unit. So it's a carbon capture unit because you're capturing the carbon from our steel mills. There are several such examples. What I would do is I would invite you to consult Climate Action Report. So if you Google Climate Action Report for ArcelorMittal, you're going to find all of these information, but also a lot more. Okay. I'm representing ArcelorMittal, but I'm also representing global R&D, global research and development, where we are roughly 1,700 researchers, out of which roughly 800 are currently in Béziers. So that's where the historical R&D base has been. We spend roughly $300 million every year on research. So that really means that we are preparing for the next 10, 20, 30 years, while our colleagues at the production sites are really managing the day-to-day operations and production-related KPIs. So we are, all our researchers are spread across 14 different geographical sites. We're not working on only metallurgy. You can say, okay, you're a steel company, you should work on steel, metallurgy, and so on. But no, steel cannot be made just because we know metallurgy. We also need to know process industry. We need to know energy systems. We need to know automation. We need to know mechanical engineering. We need to know civil engineering. data science, of course, optimization, chemical industries, and so on and on. So we basically, if you enter global R&D, let's say an example could be in Mézières, out of those 800 colleagues, I think you will find almost all the research backgrounds or all the technical backgrounds that you have in INSA or any other engineering school. Okay, just some numbers, and this is where we are right now in terms of R&D sites. So in Belgium, in Luxembourg, in France, in Spain, in Germany, in South America, in North America, in Japan, and so on. So we are really also, we want to have a diverse view. We cannot expect that one kind of thinking will lead to all the breakthroughs. So we need to have a diversity in our group. And so this is a very good example. We are really coming from all across the world. Many of us have PhDs. Right now, for example, in Mézières, we have more than 30 different nationalities present. Some of the flags here. And of course, creativity and innovation is besides safety of our colleagues, creativity and innovation is one of the key values that we have. Some of the drivers, as we talk about what will drive us for the next 5 to 10 years, we have many different drivers. Some of them are here. We are changing the way people move. So that's what we call mobility transformation. You're seeing much more smaller and ultra, let's say, local mobility. So it could be the bicycles, but also advanced bicycles. It could be the smaller cars. It could be the transport, the public transport. It could be so on and on. So people are moving away, and people are also electrifying the way that they move, right? AI is going to play a role. It's already playing a role, a very important role in our industry. But what I would say is we have been doing AI. Almost all of you have been doing AI for many years. It has a different name today. We are calling it AI, but we have been calling it advanced informatics, or you can call it regression. Anyone who has done linear regression in Excel is doing basics of AI, let's say. Okay, but what we're trying to say is AI cannot do everything. We need to be able to do the physics and the chemistry and the mathematics, and then add a layer of AI to help us accelerate our and reach our challenges. Okay. We are working on product differentiation. So that means all the steel that we used to make 10 years ago, we're not making them in those steel families anymore. Okay. Steel is not one single kind of steel. Steel is thousands of different varieties of steel, what we call steel grades or steel alloys. Some of you have studied them. So those alloys are not constant. They have been continuously worked and reworked to be able to be lighter, to be able to be produced at a lower energy and CO2 footprint, and so on. Okay, so we are continuously working on new steel grades and participating as well to the energy transition. So the steel that we used to manufacture for the solar panels, say 10 years ago, we're not making them anymore. So only this week, I think, or last week, there was a new kind of steel grade where the steel is integrating the silicon chips directly. So you have one single panel, which creates the roof, which creates the let's say the civil engineering, but it's also generating solar PV. Okay, so it's acting 1 in 3. But in order to do that, you have to allow that steel panel to live for at least 30 years. So the questions are, which kind of alloys allow you to integrate silicon chips inside them? Which kind of solar panels can live for 25 years without seeping into steel or steel chemicals seeping into and polluting, let's say, the solar panels. So you need to be also able to think global life cycles of those steels that we have. So we are really participating to the clean transition. Without steel, we'll not be able to make the photovoltaics. Without steel, we'll not be able to make the wind turbines, or whether you're for or against, doesn't matter, but nuclear, even nuclear fusion or fission, you can't make it without higher grades of steel. Okay, so we need steel to do the energy transition, and we need to be able to also decarbonize it at the same time, because we are responsible for a big chunk of CO2, which is embedded into different products, which are going to go into different industries, right? So if you're working for a chemical industry or a pharmaceutical energy company, you're going to use steel. So if you use steel, you will have a scope 3, right? So if we don't decarbonize, no one manages to decarbonize, basically. Okay, so so we need to do decarbonization in-house, but we also need to accelerate decarbonization in our final end users. And then, of course, all of this without displacing the problem somewhere else. Okay, we are very good at solving problems, but probably not solving problems holistically. Okay, so if we are going to solve the problem of decarbonization, and we should be careful in not displacing it either in terms of energy or did it disappear? It's back. Okay, so we should be careful and not be. We should be careful in keeping and in solving the global problems. So the CO2 problem is one, but we should not be displacing it towards energy. We should not be displacing it towards the SOx and the NOx or other environmental challenges. So we should be able to anticipate all of those problems and not displace the problem from one to another. Okay, so this one was for just a recall of who we are. And now let's move to how energy is used in iron and steel making. Do you have any questions? I'll cut for a few seconds, few minutes. Do you have any questions for the introduction to ArcelorMittal, who we are, what we want to do? It's clear? Okay, good. Yes.
Maybe just, it might be really great for the ECI students.
Where should I do that? Because it's not in my laptop, it's here.
Sure. Yeah, I'm sure how to do that. Maybe there. Just a small detail, but like,
Oh, there's no camera anymore because this was connected to
okay,
the
well,
pity.
okay.
Okay. No problem. So let's move into I'm here to talk about energy. So till now I've given you a global view. Let's talk about energy. So what you have on the screen is an interesting graph. On the left, what we call the energy intensity. Okay, and energy intensity is basically energy per ton of steel used. Okay, so in this case, what I'm presenting is in gigajoule per ton, but it could have been kilowatt hour per ton or whatever. And on the x-axis, I had the years. So what you see is the blue curve used to be around 50 gigajoules per ton in 1960s. Okay. So let me just try to get a pointer here. It's okay. Yeah. So you can see the 50 gigajoule per ton here. So that used to be in the 1960s, the energy consumed to produce 1 ton of steel. Okay. And over the last 50 to 60 years, many researchers before me and researchers, my fellow researchers today and my colleagues are in the steel industry, not only in ArcelorMittal, but in the group, in the world, we have worked hard to bring down that energy intensity from 50 to roughly 20 gigajoules per ton over the last 50 years. So it's already reduced by 60%. Okay. And remember, when you consume less energy, you're going to produce less CO2. So that also means the CO2 footprint has also followed. Okay. In the 1960s, CO2, we used to consume 50 gigajoules per ton, and correspondingly, we used to have almost 3 to 4 tons of CO2 per ton of steel. So that has been reduced over the last 50, 60 years through continuous efforts. Some of them are breakthroughs, some of them are more operational efficiency, but all of them have contributed to this reduction to 20 gigajoule per ton. What you see now is the green line. Okay. And trying to move my pointer. So you see the green line here at around 12 gigajoule per ton. So that corresponds to what we call the minimum thermodynamical limit, minimum theoretical limit. So that means we need at least 12 gigajoules per ton to produce 1 ton of steel. We can't escape it. Thermodynamically, we need to reduce the iron ore. We need to melt it if we need to get to the high enough temperatures. So it will correspond to the specific heat capacity, right? In order to bring the temperature of the steel, the solid, let's say iron ore, to liquid steel temperatures. Okay, so that's the minimum theoretical. So if we were going to live in an adiabatic world, where there are no energy losses and that all the energy which has been provided is being used by the process and there were no losses at all, we will only use 12 gigajoules. So even today, we are, let's say, around 50% efficient. Okay, and steel industry is probably one of the most integrated. I mean, all the losses are recovered and reused almost without fail. So what this means is there's this gap, and this gap has persisted over the last 10 years or so. There have been many improvements, but because this is a global average, the world average, okay? It does not represent what we are doing at ArcelorMittal, but this represents the global average. And that too, it only represents, let me just get rid of this. Can I? So this represents, if I remember correctly, 50%, 56% of all the steel mills have been reported. So that means 40% or so have not actually reported their numbers. Okay, either they don't have those numbers because they're not measuring them properly, or they don't want to report it because they are bad performers, maybe. Okay, so let's say the 50% are around 20 gigajoules per ton. And you can see that there's a gap, and that gap is continuously there. And that corresponds to basically missed opportunities, okay, or hard to reduce processes, okay? And those hard to reduce processes are so hard that there are no technological solutions today available. So therein lies the big challenges of today and tomorrow. And what I have presented in the, let's say, the cone is with a question mark. We don't know where we are going to end up in the next 30 years. We might decarbonize, but if all energy efficiency participates to decarbonization, the other way around is not true. All decarbonization may or may not participate to energy efficiency. Okay, so that is the risk that we're going to displace a problem. We're going to decarbonize, but we're going to increase, and that curve, which was smooth and which was, let's say, reached an asymptote, it will go back up. Okay, so you can consult some of these documents that I have here. These are not my numbers; these are public numbers. These are numbers coming from scientific articles and so on. And here, what I have is there are two scenarios how we can probably move. Either we move in the first scenario that we manage to find those in scenario one, those decarbonization technologies which are also low energy intensive. So in that case, we are probably going to go from the current blue line towards the green line, right? And the worst scenario, the scenario two, is that we do the decarbonization, but we use some higher energy intensity solutions. So that means we're going to go more towards a higher upward trend. Okay? So the risk is we're going to displace the problem from CO2 to energy. And at the energy, even though energy could be green, it does not mean that we need to waste it. Okay, so we have to keep all of this in mind. But just to, maybe the 23.6 gigajoule are the red dots that you see, which represent the ArcelorMittal numbers. We are, quote unquote, worse than the world average, but we are probably better than most of the others because we are publishing all of our numbers. We are fully transparent. So currently we are sitting at 23 gigajoules per ton of energy. So what does it represent? And this is only 1 ton of steel. 23 gigajoule represents 3 years of electrical mobility, roughly 30,000 kilometers. Or 4 years of refrigeration, or if you wanted to do binge watching on Netflix, maybe almost 7 years of Netflix nonstop, or 15 years of computer time, or if you were really a very clean person, maybe almost 50 years of nonstop washing. Okay, just to say that this is 1 ton of steel. Okay, a car typically has around 1 ton of steel, maybe more. And how much do we produce? We produce almost 70 million tons of steel in ArcelorMittal. In the world, we produce 1.5 billion tons of steel. Billion with a B. Okay. So here, what I've presented is some of the ways that steel can be made. Okay. I'm going to bring back my pointer. Is it still there? Okay. So here on the left, you have different sources or different raw materials. You need, of course, iron ore. Okay, you need coal, you need some limestone, some natural gas, and some other fuels and scraps. So typically, till now, most, let's say 70% of the way to make steel is through the blast furnace route. Okay, so you take the iron ore and you take the coal, and then you pre-process them, you prepare them in the sinter plants or the pellet plants and the coke ovens, and you bring those into a blast furnace. So blast furnace is nothing but a countercurrent chemical and heat reactor. Okay, so you're going to feed these raw materials from the top, and you're going to feed some kind of hot gas from the bottom, and you will have the reduction process, the thermal reduction process, but you're also going to heat up and melt the iron ore, and so at the end of it, you come out with pig iron. Okay, so that's basically iron without the oxygen. There are some carbon molecules attached to it, so that's what we call pig iron. In French, it's called foam. Okay, so once you have that liquid iron, that liquid metal is taken to the steel shop. Okay, so once you bring it to the steel shop, you're going to reduce the amount of carbon by injecting some oxygen at very high temperatures, and then you're going to reach the minimum steel, let's say the basic steel, but it's not finished yet. You need to fine tune the recipe. Just like in a kitchen, you need to add the different spices. So that's what you do at the secondary metallurgy or the refining process that you see here. Okay, so once you've attained the right kind of steel grades, it's still liquid. You can't use liquid steel in order to make your automobiles, right? So you need to solidify them. So you need to solidify liquid steel in what we call continuous casting. So you go from liquid steel to some semi-products. So those semi-products could be different shapes, different sizes. So let's say a slab is roughly 25 tons of steel, solid steel, 10 to 12 meters long, maybe around 1 to 2 meter wide, and 20 to 25 centimeters in thickness. Okay, but you can't even use that because that is still too broad. It's a bulk material. So what you need to then, typically you hot roll them or you cold roll them, and then you need to galvanize them, and you need to do all kinds of finishing processes in order to go from that 25 centimeters to less than one millimeter in thickness. Okay, so 25 centimeters to 1 millimeter or even less. So you really have to imagine that I'm going to take an analogy of the pasta maker machine. So you have this big block of, let's say, pasta dough, and you need to laminate it, you need to roll it so that you reach the final thickness with the final qualities and so on. Okay, it's not done because after that you need to galvanize it. So that means you need to add a layer of zinc or aluminum or some other material which is going to protect your steel against corrosion. You need to also paint it. You need to do all kinds of special treatments towards the end. Steel also produces lots of byproducts or co-products. Okay, so all the gases that we produce, so blast furnace produces blast furnace gas, coke ovens produce coke oven gas, or converter produces basic oxygen furnace gas, and so on. So all of them are recovered, reused in our processes. Okay, and whatever is left, it is typically taken to a power plant where you go through a typical gas turbine or a combustion system, produce high pressure steam, produce electricity and steam, and it is reused in our plants. Typically, steel plant is like half a nuclear reactor. Okay, so that we are talking of hundreds of megawatts, hundreds of maybe almost 1 gigawatt power is typical of a steel plant, like in Dunkirk or in Fos. And in terms of byproducts, we talked about the gas, but for example, we have solids such as we have slags. So those slags are reused as well for the cement industry. So our byproducts, our end products are reused by the cement industry, and sometimes their byproducts are reused by us. So that means internally we are symbiotic with other industries. Okay, again, I don't know if you're familiar with this kind of representation, but this is what we call the energy Sankey diagrams. What it's showing is for each process, what are the inlets, how the energy is coming into the system and how the energy is going out of the system. Okay, let's take a small example. I'm going to just zoom in on the coke plant. So the coke plant is basically doing the pyrolysis of coal in absence of oxygen to create coke, and that coke is then used as a reducing agent inside the blast furnace. Okay, so here what we are using is we're using already the blast furnace gas from the blast furnace, the coke oven gas from the coke oven itself is being fed into coke plants. Coal is there injected as well. And then you can see on the right hand side in the red arrows, you can see the different places where energy is coming out. Okay, energy is already coming out in the form of coke oven gas, which is reused. In case of coke, in case of tar, in case of waste gases, heat losses, and so on. Okay, so if you go and so all of these numbers are in megajoules per ton. Okay. So if you go and read about these kind of things, you're going to find that there are still some places where we are not able to recover the energy, and that energy basically corresponds to that gap that you saw earlier between the 20 gigajoule and the 12 gigajoule that you have. So that's the 8 gigajoules, which kind of corresponds to all the waste energies that we still have in our processes, which we are not able to capture right now because of lack of technologies, or because it's so very difficult to recover energy from something which is solid or liquid at 1200 degrees or 1600 degrees. If you just put a heat exchanger on top of it, it's very difficult because the heat exchanger is going to be destroyed within a few weeks. A typical heat exchanger would not work, simply. So you need to imagine new kinds of heat exchangers which are not on the market in order to hit those higher temperatures. And we are also talking of very high energy fluxes. We are talking of hundreds of thousands of normal cubic meter per hour of gases. We are talking of highly, maybe let's say very high temperatures or dust or pollutions and so on. So you need to be able to manage. So these are just some images. Can someone tell me what is what? Just some guesses. A forge, okay. What else? On the left, you see some liquid which is being poured into a vessel. So that is an example of liquid steel being poured into a ladle in the steel shop. On the top, yes, so that's coke. That's hot coke which is coming out of the coke oven. And right now it's very difficult to recover energy from this, because if you just put a radiating panel on top of it, you're going to recover 1% of all the energy. All the energy is still inside the coke. Okay. In the middle, you have the steel shop itself. Let's say this is a converter, and typically you have gases coming out of it. So if you don't have the right kind of gas recovery systems, it's very difficult to recover this gas and reuse it inside our steel plant. On the bottom, you have what we call a billet. It's coming out of after the casting. Once you have cast, you've gone from liquid steel to solid steel. You have cast these semi-products. Okay, so these are just some examples, but there are many others that you can find in literature. We quickly talked about CO2. So steel industry in general is responsible for 7% of all the greenhouse gas emissions. And typically all the CO2, there's an example of the footprint of CO2, where lies which process is responsible for what kind of CO2. Okay, typically 60 to 70% is at the blast furnace level. That's why you can hear a lot about replacing the blast furnace by reducing direct reduction plant, or through electric arc furnaces. Nevertheless, steel industry is far more efficient in terms of carbon intensity as compared to many other let's say industrial products, be it aluminum, be it titanium or nickel or zinc, and so on. And probably cement is the one which has a better footprint than steel. At the same time, it's not like by like. You can't replace 1 ton of steel by 1 ton of aluminum, because you will not have the same properties. So you can't, let's say you have, you want to create an automobile by 1 ton of aluminum, you'll have trouble having the same kind of rigidity, having the same kind of performance, having the same kind of mechanical performance. So you'll probably end up using 2 tons or 3 tons. I don't know. I haven't done those calculations, but you'll probably end up using more. Or for example, you had guardrails on the highway. If you want to use concrete instead of steel, you'll probably have to create a whole wall. So you'll end up using more concrete than steel. Okay. So at this current state, we understand that, of course, steel has the 2 tons of CO2 to manage per ton of steel. And there are different ways of reaching it. So we have a big target in front of you. So within all of this context, we talked about energy, we talked about CO2, and we want to propose this project to you within the ECIU framework, where we want to understand how solar energy can be integrated into the steel industry. And solar, not solar PV, we want to integrate solar thermal. Okay, so you have heard about solar thermal energy. People in the room, have you heard about solar thermal energy before? Yes. So maybe hot water out of solar thermal. Yeah. So you have those solar panels. Everyone has heard about photovoltaics. Yeah. Okay. Some of you have heard about solar thermal. So what we want to focus this project on is the solar heating applications. Solar energy can be concentrated, and you have an example of it in the picture, as a matter of fact. Okay. So you can reflect. If you go on YouTube, you will find many different videos of people trying to bake a cake using solar energy, okay, without converting it into electricity. And it's a rather simple way of doing it. A greenhouse is basically something like that. You're absorbing solar flux. Okay, this building actually is also using solar thermal energy. But what we want to do is use multiple reflectors, which are going to reflect that energy to what we call a receiver, which is the shiny part in the middle. Okay, and all of that, when you arrange your optics correctly, that receptor can reach beyond 1500 degrees, maybe even 2000 degrees Celsius. Okay, so you can definitely melt steel there, but the problem is, how do you bring iron ore to that place? How do you do the logistics that we have today, and so on? Okay. And we're talking, again, not of 1 ton of steel, we're talking of millions of tons of steel per year in one site. So the challenge is, there are many challenges, and therefore the plant of the future could be, let's say, driven by our carbon neutrality goal. This is just an example, this is just a caricature of what it might look like. You have the tower in the middle, you have panels, not solar PV panels, but solar collector panels. Basically, these are like mirrors, which are going to reflect solar rays towards the concentrator. Okay, and then once the heat has been concentrated, you can use it for different industrial purposes. Okay, so the aim is that you determine the different ways to integrate solar energy, and that to solar heat, not solar photovoltaic, solar heat in iron and steel making processes, either the existing processes or the new processes which are being developed right now. They could also be beyond the scope of steel industry. They could be through carbon capture. They can be in hydrogen production. They can be in different ways. But that should be your solutions. Okay. Once you have done your analysis of the problem, once you have reached that level of maturity, you will find that these solutions will come up. Some open challenges that I can propose to you right now. Okay, but again, this is not an exhaustive list. My understanding would be that you will be going through your project, you'll be also identifying other open challenges and then solving those open challenges. So some I have noted. One of them is how to ensure that the heat that is available at the solar tower, which is beyond 1000 degrees, even in some cases 1500 degrees C, that you don't reduce that. I don't know if you're familiar with the concept of exergy. Someone? Exergy is basically the quality of energy. In another way, it's the temperature level of energy. Okay, 1 gigajoule of energy in a glass of hot coffee is not equal to 1 gigajoule of energy in hot steel. In some cases, okay, the temperatures is different. So the concept of exergy comes there. All right, so my proposal to you, my challenge to you is not to come up with ideas where you're going to use solar to heat water at 90 degrees C. We have other ways to do that. Okay. If you have energy source at 1600 degrees C, we should be able to find energy uses at between 1000 and 1600. That is where you will have the maximum benefits. Right? If you have solar energy available between 600 and 1000, you should be able to use that energy between 400 and 800. If you bring that energy down to 80 degrees, that's just making hot water out of such a big infrastructure. That's not useful at the end, because what will happen is you will probably generate hot water, but for the industrial purposes, you will reburn natural gas, or you will burn again some other fossil fuel, and you will defeat the purpose of adding solar. So first challenge, how to keep the energy levels high enough, maybe above 600 degrees C. Second challenge, how to integrate solar thermal energy into brownfields. We will not be replacing all our industrial parks by new places. So we have existing industrial infrastructure. How do we integrate solar energy into those existing industrial brownfields? Okay, so that should throw up problems. That should throw up challenges to you. How to work on space available? How do you integrate while respecting the current footprints? You will have problems related to how to find solar energy, how to make it more compact, right? And by definition, if it is more compact, it has lower capital expenditure, so it will cost less, and it will be easier to integrate into your existing industrial infrastructure. Third is the intermittence. So that means solar energy is not available all the day. We know that. It's not available homogeneously across all the seasons, right? And on top of it, solar energy can be disturbed by events, right? You can have some black swan events. You can have climate events. You can have political events. You can have economic events, and so on. So you can have those intermittents, natural or man-made, on the source side, but you can also have intermittents on the steelmaking process. Steelmaking process is not a continuous process. As a matter of fact, there is no steady state. There is no steady state in steelmaking. All the processes have their own transient states. So you have to understand which transient state. So that means your energy source is also transient. Meanwhile, your energy sink is also transient. So you have to manage let's say, unsteady nature of both in order to find solutions which work both for the energy source and on the energy sink. And then those energy source temperatures and your energy use temperatures should match. Okay. Again, you can't take energy at 1200 degrees to satisfy needs at 80 degrees. That's not good use of the energy that you have. Another maybe recommendation could be, you can, instead of looking at the steel industry fully, because you will have trouble finding during your project, maybe you can choose one area, or maybe you can choose one process. Okay, you are free to choose which process you would like to work with. Each process has their own, as we saw in the Sankey diagram, has their own influx of energy and outflux of energy. So you can choose. So this is, let's say, you can just focus on the hot rolling, or you can just focus on the coke plant, or you can focus on the DRI, or you can focus on the blast furnace, and so on. Up to you. So the choice is yours in that way. Also, there are many different solar technologies already available on the market. Again, up to you to match those solar energies with the process. There will be some solar energies which do not produce 1600 degrees heat. They only produce steam at 400 degrees or 200 degrees. But then maybe you can match it with some industrial process which needs the steam at 250 degrees. Okay, so, okay, but that should be part of your thinking process, and that should be part of your resolution of problems. So I'll stop here and then open the floor for some questions, because I know that you have classes after this.
Hey, I told you it was One project. Now that you have this explanation, open questions. Yes.
If you don't mind, would it cost you?
Speak louder in order that the microphone will hear you.
Was only saying, if you don't mind, if it could be possible to start a statement.
Yeah, I'll share the documents with you guys.
Okay, good. So document will be shared, including the video that is normally played. Any other questions?
Feel free because I'm here and
Yeah.
I'm here primarily to receive questions from you.
I have a question.
Sorry, someone is asking, and then I'll give the floor to you. Yeah, go ahead.
Sure.
Up to you. If you feel that in order to satisfy the intermittence on both sides, that the storage, energy storage is one way of, let's say, solving that problem, maybe. But that should be part of your reflection once you have identified the real problems. Okay, storage could be good, but they can also create other problems. Sorry, there was someone on the.
Yes, I had a question regarding, based on my understanding, what I heard is to us right now currently is really important to consider the energy and the use of energy. So is there any point of regarding the cost, like the money wise, or basically also regarding to the logistics? How much we are limited there, or for now we are not really limited in that case?
So what I would say is CapEx should always come as a criteria, but it's up to you. You can choose to disregard it, but it should be clearly written that, okay, we are not going to manage the CapEx right now because you're not an engineering company. You will not have CapEx for all the equipment. So you will have a tough time finding all of those numbers. My proposal would be to look at it from heat point of view, from fluid point of view, from energy point of view. The logistics could be an interesting thing to take into consideration, because that would mean how do you move energy from one place to another? So that could be part of your logistics. The logistics that you may not be able to manage right now is how do I don't know, move iron ore from one place to another? That would be more complex and not necessarily within the scope of your project. So as long as the logistics has to do with how do I move energy from the solar plant into the steel plant, or how do I move, let's say, the process towards the solar plant? Okay, maybe you can consider it in your reflection. CapEx, what I would say is if you reach a point where you say the only problem left for me to solve is the CapEx, then that's already a good thing to do. So that means that we have converged towards CapEx. But don't take it as a limiting factor right now. Okay, let's say we have unlimited amount of resources, right? But at the same time, if you manage to find solutions which are not displacing the problem, which are low CO2, which are managing to have high enough temperatures and are compact enough, but also low CapEx, even better.
Okay, thank you very much.
Sure.
Other questions?
Go ahead.
So solar technologies that are right now on the market.
Yeah.
You can use them to step up the steel industry, even though the temperature is below 600. Is I think that we need because in the situation we said that.
That's true.
So okay.
That's true. But at the same time, there are other processes Like if you really look at all the processes inside the steel industry, you have other processes where some low temperature solutions might connect with low temperature needs. My proposal to you was to maybe concentrate on above 600 because that is where the big challenges are. But if you decide not to focus on that and you want to work on lower temperatures, you're welcome to it. It will be a lower, let's say, in terms of challenge, it would be a different kind of challenge. It would be more probably through integration, how to make it more compact, how to, let's say, integrate it into existing solutions. Or how to bring back the used steam back into, so how to create a loop. Okay. Meanwhile, on the higher temperature sides, you will have a different challenge. Both are equally challenging. My feeling is lower temperature solar solutions are already higher TRL at higher maturity. So probably you'll be able to use them tomorrow and you'll have less, maybe, I don't know. I haven't tested it yet. Maybe you'll have less contradictions, maybe, or maybe you'll have more contradictions. And the other one, the higher temperature ones are not yet solved. Okay, so you will have probably more contradictions. It will be more challenging, but probably if you find solutions, they can be more rewarding. You choose.
Can we continue? Any other questions?
Online.
Okay, let me ask and comment with you the objective of a challenge. The challenge is also that they will constitute teams and how it will happen, the evaluation stage. The experience we had last year was a little bit different because there was only a single group.
Yeah.
We only do a small quantity of students. Here, you will probably be divided into 14, 15 groups. At the end, there will be an oral defense, like a Viva, and let's say 15 minutes of presentation, a few slides, PowerPoint or whatever. What are you expecting to be surprised in terms of how will you evaluate that something is interesting for you?
Okay, so maybe one of the first things that we're going to look at is how well have you understood the problem? And where have you gone with it? I mean, have you looked at it at a very superficial level? Okay, or have you gone into where and how the energy needs to go, in which process, and at what temperature points, and so on. So your problem, let's say problem statement, and how well you have defined your problem statement is one of the evaluation, and probably ideas to solve those problems are, it's an important point, but for me as a researcher, I would rather look at how well you have understood the problem. And in order to understand your problem, of course, some of the information was given as a flavor today, but you will have to read, you will have to go through some literature, you will have to do your own research. You will probably be using the Finder tool in order to identify, maybe through patents or through articles or through scientific documents, what others have done and how they have been partial solutions.
This was another question.
Yeah.
This domain, is it covered by patent and scientific article? Widely, not so much.
Not so much. In my understanding,
we find patents solve such problems?
In my understanding, you will find patents on the solar side, but not too much on the integration with heavy industry. Yeah. So
and scientific papers, articles?
Very few. So you are really working, or you're going to be working on things which probably you'll be the first ones, let's say, to think about it.
When we see your slides, we also go through internet and we see solar farms. So
Yeah.
What is the existence, your knowledge about what exists already today, which would be the closest to your expectation? Not what you expect fully, but the closest.
Yeah, so there are solar farms. We just saw that there was a solar farm inaugurated in south of Spain by Heineken. It was developed by NG and some of the other energy players. But what they're doing is they're using the known technology to produce steam. And that steam is used in beer making. Okay, good, because their process needs steam at 10 bars or 15 bars. So that's a good example, but it's rather limited because it can only be applied to less than 1 gigajoule in our situation. It doesn't cover the 20 other gigajoules that we have. Okay, what that means is if you were only to produce steam, that steam is useful in maybe one process or two processes, and that's it. You'll not be able to use it to melt steel. You'll not be able to use it to do pyrolysis of coal, or you'll not be able to do preheating of materials using it, and so on.
For example, say, how can we understand, for example, that we have what we call some solutions, and the solution already exists, and we not use them, we avoid using the same solution or to try improving them. How can we understand what you?
Yes. So I think Finder can help you with that. When you're going to construct what you call the knowledge map. Okay, in a knowledge map, you will see which solutions exist and which solutions are displacing the problem to some other problems. Okay, so there are existing solutions to produce steam from solar. There are some existing solutions. If you go and look for a laboratory in the Pyrenees, probably you've heard of it. There are solar towers which have been developed in the Pyrenees by CNRS. You will see that there are solutions, but then the solution is just standing alone. There's no, either it is used for energy production in terms of electricity, but there is no direct integration into industrial process. Okay, so maybe through when you're building your knowledge map, when you're building your questions, you will find through papers. So you'll have one part of the problem would be how to go from sun to some heat through solar tower or some kind of solar technology. Then the second part of the problem is how do you go from that solar heat into process heat, and where, and how much, and when? Do you need to store it? Do you need to use it as it is? Maybe you also need to look at how you can combine it, with other energy sources, other renewable energy sources. Okay. And you asked me that question, and I'm going to just follow up. So you asked me the question: how are we expecting to evaluate?
Yeah, it's important because it could constitute a goal and a strategy individually by group.
So one of the intermediate deliverables that we can expect from the different groups could be your knowledge maps, and you can imagine it being constructed in somewhere in the middle of your. How long is it going to be? 1 year? 6 months?
No, it's a semester.
1 semester. Okay.
That's 24 hours.
Okay.
And by pieces of two all along the semester. So the time is rather limited.
Your time is limited. So what we can say is you will spend some time on understanding your problem, on examining the literature, on really going from this statement, very simplified, to your part of, you can choose different parts. You can choose, so as I was saying, the intermediate deliverables could be the knowledge map itself. Okay, that could be your somewhere in between, and the final deliverable will be your knowledge map plus
Set of contradictions.
plus some contradictions or some ideas even.
So the flow, they start to know a little bit because we did 2 hours with each groups.
Yeah.
Knowledge map, a few description. Switching from knowledge map to set of contradiction is one thing. And from contradiction to the use of knowledge in order to generate ideas
Is
the
another.
last step.
Yeah.
So if a compilation of those 3 steps with knowledge map, key contradictions out of the knowledge map, plus interpretation of association between a contradiction and an information that is likely to solve it,
Yeah.
and transformed into an idea, a solution. And this solution relevance will be useful for you, maybe if it goes out of the brainstorming idea you already had, because it needs
Yeah.
to surprise you. It needs to bring you
Yeah.
something new.
So just for example, we've already worked on this topic internally using some of the techniques that you're going to test. Okay. So one of the ways that we can look at it is, as Denis is saying, are we surprised by the solutions or the ideas or the reflections that we're going to make?
Yeah.
Because we've already done those things. So if we find, what we are hoping is maybe 80% of it would match what we've already thought about. My expectation is, because we are a much diverse group, you will have different points of view, and that is what we hope to have. Your points of view would be completely different to mine and my colleagues. Okay, so and secondly, experience is good, but experience also creates bias. So my experience is good. I have more than 15 years of experience, but I will have my own internal bias, right? Maybe I'm subconsciously pushing the solutions towards more heat or something else without knowing it. So I want to avoid those biases by opening the challenge to you, because you guys will have a different view without the biases, hopefully, to the same problem. Yes.
That's what you said, even why there's no thermal engineers in the session.
No, I didn't know. I didn't know who was going to be part of the group today. That's okay. We didn't. I didn't plan for that. Okay. If any other questions in the room?
I have one small question, and regarding to follow-up questions regarding the challenge. How can we contact you or the company regarding the follow-up question, basically?
Yeah, I'll leave my email and you can contact me through it.
Okay,
One,
thank you.
and secondly, what we can try to do is either towards the end of the year or early in January, I'll open let's say a Q&A, and let's say we can do that rather easily. We can send a Q&A. Anyone drops in, you can send or you can speak to me directly. I'll make sure that I'm available for, let's say, 2 hours. You can come, pose your question, and then go.
Okay, thank you.
Yeah,
Sure.
As a start, in order not to have maybe a too wide spectrum of info to compile, could you point to specific literature that you think it's useful to read, like an article, even a journalist article? Have you ever had an article written by a journalist summarizing this problematic and
No.
explaining it to the world?
Unfortunately, there are no articles to my knowledge where there come. Unfortunately, to my knowledge, I don't know of any articles which combine steel industry with solar energy.
Okay. No journalists have never investigated that problem.
Maybe they have investigated solar photovoltaics. Maybe they have investigated the use of steel in building the solar tower or solar panels, but not necessarily process plus process.
Okay.
What I can do is I can share with you some articles on the basic understanding of energy use in steel industry, where energy is used or where energy is lost, or where energy is not properly used maybe. And I can also share maybe some articles on solar energy, solar thermal energy as well. So I can share those. it's up to you to be able to match those two worlds. Those two worlds have existed independently till now. My hope is that we're able to bring them together.
Okay. No more questions?
Okay, maybe I have a couple of questions.
Okay. Go.
So has any one of you been to a steel mill or a steel plant?
Yes, Cedric. Cedric, you.
One, someone? You've been to a steel plant? Paper mill. Okay. Paper mill has some elements which are similar to steel plant, but it is still very far away from. You can have processes related to lamination, hot rolling, and so on, but not necessarily. Anyone, any other industry that you have been to, seen in real life? No? Okay, so that is something that we should also try and correct. Yeah. I don't know how and when it could be possible, but we can try to organize something.
Yeah, I can discuss with Hakim Remita, see if plant visits are
allowed.
Yeah, are allowed. I believe so because it's tradition also sometimes to go up. If it's in the pipeline, in the process, I discuss with Hakim and see how we could organize that.
Could that be of
It's
interest?
1 hour drive from here, so it's not too far.
The nearest full steel plant would be maybe in Luxembourg. Or no, maybe on the German side. There are some steel plants, but not with us there. Uconge, Florange, we only have downstream processing. So that means you only have hot rolling and beyond.
Okay, let's discuss.
Yeah, so let's discuss that. Another maybe question for you guys. What are your expectations from this project? What are you here for? Discover a new field. Okay, what else? Be candid. You can be free.
And also try to find these talents, find out it, and have some solutions.
Okay.
And to think by other way, then I fully understand how we can resolve this problem. Before it's complicated for time to find out the solutions.
Okay.
We have one problem. It's obligatory to have one solution, or if we don't have one solution, it's not a problem. You know what I mean? Then we try to find out something that we don't escape.
Okay. So thank you. Any other? Yeah. Okay. Good. What else? Okay. Okay. Good. Maybe what I heard, it kind of invoked a couple of questions for me then. How many questions are you expecting to see in your understanding? Like, are we talking of one question? Are we talking of many questions? Many questions. How many? Seven. Okay. How many questions? When I think of this problem, yes. At least 20. Okay, good. When I look at this problem, I am expecting at least 100 different problems, maybe even more.
One of the curiosity I have, because last year we only had one group, is how they will divide by themselves, right? By problematic situation. I don't expect to have 14 parallel teams working on the same topic.
I hope not.
No. So there is a first obstacle for us is to choose on which sub-problem or on which array of this big problematic a group will decide to go. And there should be as many topics or subtopics as groups, in fact.
Yeah.
So you, at the end, you would have not 14 times the same presentations, 15 minutes, but each time a proposal, which could constitute one part of the puzzle of a bigger problem.
That is my hope,
Yeah.
but the difficult point would be if, let's say if some group decides to work only on the energy storage, okay, but you will have some trouble only working at it in an isolated way. You need to work on the solar part. You need to work on the process part in order to really understand the storage part, right? So
Storage is already a big problem.
storage is a big problem, but what I mean to say is you will have some difficulty in narrowing your scope because all of it will be interconnected. But one way could be team by team. So, or let's say process by process. You have seen many different steel processes. You can choose to work on one, or maybe if you are 14 groups, and this is just a proposal, okay? You can decide that there will be 2 or 3 groups which will work on one process, and 2 or 3 groups which will work on another process, and so on. It could be one way of doing it.
This, how much energy the process.
Yeah. Sure. Yeah, absolutely. Yeah, so those are some of the numbers. You remember the energy intensity graphs? There were a couple of documents there. If you click on those 2 documents, you will already have a big part of the numbers. And if you want more numbers, I have different public journal articles available for that. Okay. Yeah, there's another thing. How many solutions are you expecting? Looking at the problem that you saw, and some said 5, some 7, some 10, some 20 different questions. How many ideas or how many solutions are you expecting? Rough ideas. I'm not talking of the final ideas that you're going to probably implement. Are we talking of one idea per group? Are we talking of many ideas per group?
I think they have no clue about that.
Okay.
If you're referring to brainstorming is a long list.
Yeah.
And I'm not going to follow that.
Okay.
The idea is an idea is relevant to be proposed to you
Okay.
as long as it's not a compromise,
Okay.
and as long as it is inventive. So there will be a filter, and my expectation due to the time limitation we have
Okay. Then it's
will
good.
be not to exceed 3 or 5. And among the 3 or 5 per group, I wish one will be put forward as their solution. So I want to associate, maybe each group should have from 3 to 5 ideas to propose, but then we need to say, this one, we put this one forward.
Okay.
And the idea will be associated to the group.
It is mandatory to use a TRIZ method to find solutions on this problem.
That's the goal. It's mandatory, you have no choice.
No, but you will see, freeze is one part, but the problem identification, the contradiction is common to all the.
There is classical project management, but if you want to differentiate compared to a classical brainstorming that they have been doing 100 times, maybe the idea to use TRIZ is to, if you go abroad, grabbing some information from other disciplines, TRIZ will be helpful for that. So it will help you to associate your problem to a different domain in which there have been successful solutions. This association brings you new insight that is a kind of guarantee of inventiveness when you propose ideas.
Yeah, but the idea is also to brainstorming with people that are not in the field of steel manufacturing. You also if we just do brainstorming but without any knowledge in this kind of field, we can raise some new solutions, problems. Maybe that it's impossible for people in this field to find because it's.
That's why TRIZ will be a way to go out of the domains. That's the final idea of TRIZ, cross domain. So that's the.
Your hypothesis is that you're a different bunch who have not worked in the same industries. So probably you will find new ideas which are, it could be true. But generally when you produce lots of ideas, before it really gets to an inventive idea, you will spend a lot of time. And generally, if you use TRIZ, you will get to that point faster. So that's why you're proposing it through TRIZ.
Yeah, the goal is definitely not a brainstorming.
You can probably have the same ideas, but you will need to generate 1,000 ideas in order to find the 5 ideas which are probably invented. Meanwhile, with TRIZ, you can probably do 10 ideas in order to find the 5.
Simply transforming your problem into a contradiction is a part of it. If you only use that part of it, transforming a problematic situation, which is defined as a very broad spectrum, transform it into accurately defined contradiction will be a good one. Just that.
Okay.
Okay, so if we are done, we need to thank you. Thank you, Sure. There are no more questions, we will see. We keep in touch with you.
Yeah. I must also thank you all for listening and then also participating. I hope that this was of interest and that you have learned something today and that you will continue to learn new things about steel and solar.
Okay, thank you to SAIU people, and we keep in touch for the coming days. Bye.
Bye-bye.
Thank you.
Thank you.